In the area of science and gigantic mysteries pertaining to what was previously before the gigantic explosion, conversations have blended and intrigued characters for quite some time. This enormous question doesn't just test how we could decode the universe, which is difficult, to the actual boundaries beyond which human knowledge stretches. Imagine standing at the edge of existence, looking into the colossal shadow, and pondering what lay there before our universe was imagined. The event of the Big Bang marked the beginning of time, space, and all that we know. But was there a second, earlier in the past? This might have been a state of being nothing, a calm before the cosmic gathering started. And if this is true, was it? Or perhaps was there something much more alarming that existed previously before time itself? As we jump further into this question, science takes us on a journey past the insights into the beginning of the universe, insights that challenge our consciousness. Physicist Brian Cox, well known for his investigations into the wonder of the universe, suggests that something surprising might have existed before the enormous detonation. He moves us to reconsider our thoughts on reality in existence. In this examination, we'll dissect the theories, the research, and the dazzling secrets that might make sense of what existed prior to everything. We'll investigate ideas like self-important, development, quantum changes, dark energy, and even multiverse. The responses we find might just paralyze you, yet they could likewise open new understandings of our position in the universe. Get ready to dive deep into a world beyond imagination and science in the midst of the obscure. Scientists studying shadows were shocked and sometimes even upset. We ought to explore what existed before the Big Bang and why these theories challenge all that we thought we knew. To appreciate what may have existed before the Big Bang, we first need to painstakingly analyze what the Big Bang truly was. The Big Bang, as scientists define it, refers to the moment when the universe became extremely hot and dense, growing rapidly to set off the development of all matter, energy, and boundless forces. When we look toward the night sky, it reveals evidence of this rapid start, with galaxies spreading out in every direction from an early starting point. But for what purpose did this occur? Was there a period before this dense, hot start? According to the theory of enormous expansion, there was indeed a time before, and it was not even close to void or peaceful. Vast expansion suggests that before the Big Bang, the universe was in a state that was cold, empty, and unorganized, essentially like an immense vacuum. However, this vacuum wasn't entirely empty. It contained a gigantic amount of energy that fueled the quick expansion of space itself. This expansion, called inflation, happened so rapidly that it essentially established the groundwork for all that would follow, parts of a subsequent space extending at unfathomable rates until the expansion slowed down and the energy transformed into matter-like atoms and the forces we recognize as the Big Bang. But what was the nature of this energy? Why did it suddenly grow the universe, and why did it prevent experts from believing that? This enormous expansion led to patches of the universe, each experiencing its own Big Bang. Imagine a fabric that extends indefinitely, with minuscule air pockets forming here and there, each air pocket representing a universe, including our own. This thought, called the inflationary multiverse, suggests that there could be limitless Big Bangs and an infinite number of universes. Our own is just one of many. This enormously perplexing reality challenges our understanding of the very universe itself and leaves us with the question, what else is out there? The idea of nothingness before the Big Bang is speculative and not real, as per our current understanding. Regardless of whether you eliminate all radiation and energy particles from the universe, it still wouldn't be genuinely empty. Darkness fills the void in our quantum matter, and dark energy fields and other forces combine to form an inevitable artwork embroidered with something, even in its most vacant structure. Regardless of whether we imagine stripping away all of these forces that render the universe a dead space, it would still generate new kinds of energy. This reality alone is bewildering to experts because it suggests that true nothingness might be impossible within our infinite comprehension. Space itself has properties, rules, and constants that keep it from being completely empty. Imagine creating a region with literally nothing in it. No particles, no radiation, and no energy except quantum fields and major constants. These would still exist, implying that this non-existence has properties. For example, there is a peculiarity called zero-point energy, which represents the least possible energy condition of quantum fields. In this state, particles can still momentarily appear and evaporate, creating a spooky resonance of movement even in what should be empty space. This challenges our concept of a genuine void, and yes, even before the Big Bang, there was something that scientists are only beginning to understand. One of the most astounding theories in current cosmology is the chance of timeless expansion. If inflation could cause our universe's existence, it suggests that it may continue forever. Brian Cox describes an astonishingly vast inflationary multiverse where universes are infinitely created and continue expanding. Imagine each Big Bang as a flashlight igniting another universe, while inflation continues in different areas, making countless other universes. In theory, this cycle could continue forever. This idea of vast universes and eternity gives birth to an enchanting concept, a fractal universe where each new universe may, in fact, produce its own Big Bang. Every universe exists as a separate, independent domain, unaffected by the others as a result of the rapid growth of space. For researchers, this hypothesis is both exciting and upsetting, as it suggests a never-ending multiverse with no definitive beginning or end. Imagine our universe being just one bit in a giant cosmic structure, forever expanding and constantly creating new universes. And what if the upsetting fact is that there is no before or after, but rather a timeless pattern of universes forming and decaying? Our understanding of nothingness changes when we consider quantum field theory. According to this theory, the universe is not just an assortment of matter floating in space. Rather, it's a complex network of energy fields that fill the universe, connecting to create all that we observe. These fields are like invisible seas, with particles acting as waves or disturbances. Even when fields are at their lowest energy level, known as the vacuum, they are still alive. Particles can appear and disappear in these fields momentarily, acquiring energy before returning it. This phenomenon results in virtual particles, substances that immediately exist and then vanish, leaving only a faint memory because of their presence. The notion of virtual particles challenges the idea of a real void. Imagine an empty universe where all energy and radiation are eliminated. Would you have total nothingness? According to quantum field theory, you wouldn't. Even in a vacuum, fields would remain active, sometimes creating transient particles. This constant movement in what should be nothing implies that the universe does not. Gravitational waves, ripples in the fabric of space-time, could carry the earliest evidence of cosmic events, even those preceding the Big Bang. These waves are produced by powerful cosmic processes, like black hole collisions, but if we could detect primordial gravitational waves, they might offer direct evidence of phenomena that occurred during the universe's infancy or even before it. Scientists theorize that if a previous universe collapsed, perhaps in a cycle as proposed by the cyclic cosmology model, the shock of that collapse could have sent gravitational waves rippling across the boundary into the next phase of expansion, our current universe. These relic waves would be incredibly faint and difficult to detect, but instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, and proposed next-generation detectors might someday catch their whispers, too faint for these waves. Not only would they confirm the cyclic model, but they would also provide insights into what physical laws governed the before. Were the constants of nature the same? Did time move differently? What kinds of matter and forces dominated that reality? Loop quantum gravity, another theory seeking to unify quantum mechanics and general relativity, offers its own radical view. It suggests that the Big Bang wasn't a beginning but a bounce, a point where a contracting previous universe stopped, shrinking, and began to expand again. In this scenario, space and time are quantized, meaning there's a minimum possible size to any region of space, preventing true singularities like those predicted by classical general relativity. As opposed to an origin point, you get a rebound, a moment of transformation, not creation. This big bounce model aligns with other quantum gravity theories in proposing that space-time itself is emergent, not fundamental. In other words, before the Big Bang, there may have been no time, no space, only information or quantum potential waiting to unfold. It's a notion that unsettles and excites physicists alike. If we accept that time and space are not eternal but products of deeper quantum rules, then before the Big Bang becomes a meaningless term in the conventional sense. Instead, we must think in terms of quantum states, symmetries, or even pre-geometry, abstract, frameworks not anchored to time. The search for W. The universe's previous states, the potential discovery of early-stage gravitational waves, is one of the most exciting possibilities in cosmology today, as it might not only reveal the truth about the Big Bang, but also offer a glimpse into the cosmic state before, according to this theory, the universe was formed. A tantalizing prospect, detecting gravitational waves that could act as fingerprints of a pre-Big Bang universe. As we continue to explore what could have existed before the Big Bang, we delve into concepts that push the boundaries of our understanding, putting even our most fundamental assumptions about space, time, and existence itself at risk. One of the most mind-boggling ideas comes from the realm of quantum gravity, a field that seeks to merge quantum mechanics with general relativity. This merger could potentially reveal a unified theory of everything and could provide an understanding of what existed before the Big Bang. Quantum gravity suggests that space and time are not continuous, smooth entities like we experience them, but instead are discrete, granular structures. This theory posits that the fabric of space-time itself could have been formed from a structure on the microscopic Planck scale, with tiny quantum fluctuations shaping the universe in ways we cannot yet fully comprehend. In this view, what we perceive as the smooth space-time continuum might have only emerged from these fluctuating quantum fields. Thus, the before the Big Bang could be described by a completely different concept of reality, one in which space and time themselves were not fully formed. Another possibility is that the universe is part of a vast cosmic landscape of possible universes, each with different physical laws and constants. This theory, known as the string landscape, is the result of string theory that holds that all fundamental particles are actually tiny vibrating strings. In this framework, there are numerous configuration options of these strings, each corresponding to a different set of physical laws. The string landscape could imply that our universe is just one of many, each emerging from its own distinct Big Bang-like event. The existence of such a landscape also brings forth the notion that other universes might have different dimensions, different strengths of gravity, or even different types of matter. In this view, our universe might not be unique, but rather be a part of a multiverse, a collection of universes, each evolving independently. The multiverse theory provides a speculative yet intriguing response to the question of what came before the Big Bang. Another universe in a different configuration, potentially leading to infinite cycles of development and devastation without, in addition to these, definitive origin. Some theoretical physicists have also considered the role of black holes in shaping the nature of the universe. A growing hypothesis is the fact that our universe may be the result of a black hole formed in another universe. In this scenario, the singularity at the center of a black hole could be a gateway to another universe, with the Big Bang being the moment when such a black hole gave birth to our cosmos. This hypothesis is supported by the fact that, according to general relativity, The singularity at the center of a black hole is a point where space and time curve infinitely, creating a region where the known laws of physics break down. It's possible that the extreme conditions inside black holes could lead to the creation of new universes. This may indicate that the Big Bang was merely the birth of our universe from the singularity of a long-dead black hole. Looking into these concepts requires a deep dive into the very nature of time itself. Some cosmologists speculate that time, as we understand it, may have had no meaning prior to the Big Bang. If the Big Bang was the origin of time, then there may have been no before in any conventional sense. This point of view suggests that time itself might have emerged either through quantum fluctuations or a primordial state where the usual distinctions between past, present, and future did not apply. This could lead us to rethink the concept of causality, which relies on the assumption that events happen in a linear sequence. If time did not exist in the way we experience it, then the question of what came before the Big Bang becomes nonsensical, as there would be no temporal framework to support it. Further complicating the picture are theories of cyclic time. As mentioned in the past, cyclic cosmology has suggested that the universe undergoes endless cycles of birth, evolution, and eventual collapse. In this model, the Big Bang could represent just the most recent bounce in an eternal series of universe cycles. These cycles might not be identical but could evolve in different directions, each with unique physical properties. The cycle of the universe, according to this theory, would be a continual process with no true beginning or end, rendering the question of before the Big Bang meaningless in the conventional sense. The idea that time itself might be cyclical implies that each Big Bang could be followed by a contraction and another big crunch, with the universe relaunching itself in a never-ending loop. Another avenue of investigation into the nature of the cosmos is the potential of a primordial soup of particles and fields that existed before the formation of galaxies and stars. This idea suggests that before the universe began its rapid expansion, it was filled with a dense and hot mixture of elementary particles, including quarks, leptons, and bosons, all in a state of extreme energy. These particles would have been interacting at extreme temperatures and density, laying the groundwork for the formation of matter and energy. As the universe cooled, some versions of this theory suggest that this primordial soup existed in a quantum foam where particles constantly emerged and vanished due to the uncertainty principle of quantum mechanics. The properties of this soup could potentially offer insights into the earliest moments of the universe, and by extension, of the universe before the Big Bang itself. Ultimately, what existed before the Big Bang is still among the most profound mysteries in science. As our understanding of quantum mechanics, cosmology, and fundamental physics deepens, new theories will continue to emerge, offering increasingly complex and sometimes paradoxical explanations for the origins of our universe. While we may never fully grasp what came before the Big Bang, the pursuit of this knowledge will continue to stretch the limits of human curiosity, driving us to explore the unknown frontiers of existence. This relentless quest for understanding not only reflects humanity's desire to know where we came from, but also shapes the way we define reality itself. As scientists and philosophers push further into the theoretical unknown, the line between science and metaphysics begins to blur. The questions surrounding the origin of the universe, questions once considered purely philosophical, are being tackled with the tools of physics, mathematics, and cosmology. New advancements in technology, such as highly sensitive gravitational wave detectors and next-generation space telescopes, may soon allow us to observe the earliest cosmic signals with unprecedented clarity. These instruments could capture faint imprints left over from the universe's infancy, traces that might contain information from a time before the Big Bang. The potential discovery of such signals would mark a revolutionary shift in our understanding of cosmological history, offering empirical data where once there was only theory and experiments. At the same time, efforts in quantum computing and particle physics are pushing boundaries at the smallest scales. These efforts could uncover new insights into the quantum structure of space-time, helping to unify our understanding of the cosmos at each of the smallest and largest levels, bridging the gap between the macro and the micro. General relativity and quantum mechanics remain one of the grandest goals of modern science. Equally important are the philosophical implications of these inquiries. If time had no beginning, if space can emerge from fluctuations, if universes can spawn from black holes or exist in parallel, then the very meaning of origin requires a new definition. It challenges our intuitions and demands a broader framework for thought, one that may require abandoning long-held presumptions regarding the sequence of causality and temporality. Even the idea of existence may need to be rethought in a multiverse or pre-Big Bang scenario. The notion of a single, unique creation event may give way to a dynamic, eternal process, one in which countless beginnings and endings occur, not in isolation, but as part of an infinite, self-renewing system. This perspective does not diminish the significance of our universe. Rather, it situates it within a larger, more intricate tapestry of cosmic evolution. In the end, our search for what came before the Big Bang is more than a scientific journey. It is a deeply human one. It speaks to our need to find meaning in the universe, to comprehend our place in a vast, mysterious, and ever-unfolding reality. Whether we find definitive answers or only deepen the mystery, the pursuit itself elevates our spirit, reminding us that even in the face of the unknown, curiosity endures.